design of composite sections using multiple H-roll sections. Not too far from here, this was the construction of the World Financial Center, just next door. You can see that today the high-rise buildings are designed using super mega column here in the corners. Here is a view of the Pinhang Center that will be built in Shenzhen, what will be one of the tallest buildings in China in the near future. It's under construction right now. So they are using composite columns. This is 6.5 meters by 3.2 meters, so it's about 1/4 of this room, just one column. Using heavy plates, all welded together. All the plates are tied together. So when you have to design this type of connection, so first the difficulty is there is no exact welding procedures today. How to weld this type of section? Do you start to do the welding here? Do you start there? And on top of that, how to splice all these joints? When you have to splice them on top of each other, it's highly complicated. If you follow the welding codes, here in this case they are using 65 millimeters and 50 millimeters plates. According to the welding codes, you must preheat the whole section at 110 degrees centigrade before and during the welding. So if we saw you go to the Jimao on the top here, you can go and see now how they are building the Shanghai Center. They use the same concept. It's designed by the same designer. So they use also huge caissons, all tied together to do this mega column. These huge caissons are so heavy that they have to stack and weld each floor because the crane is too small to lift multiple floors at once. So here I took this picture during February, and here we can see this huge caisson is going here, and I just saw another one this morning because my room is exactly on the 58th floor, so I can see exactly how they are doing it. So this caisson is going there, and a few minutes later, they were welding it. At that time, in February, it was 2 degrees Celsius outside, below the dew point. So normally when you take an electrode, and when you touch the steel, immediately you have a condensation of water. After Northridge earthquake, after the Kobe earthquake, they changed the way of doing all these type of connections to control exactly how to do the welding. So according to the codes, first you need a wind protection. You need first one guy with a torch to preheat all the connection at 110 degrees. To preheat this type of connection, it will take maybe 10 hours with a torch. And then a welder can come and start the welding. If you go to the States, this is the slides from the States in New York, from a new high-rise in the States. When you see a welder, and we will see tomorrow, I don't know if you are going to see the job site of the Shanghai Center, you see they have tools all around. So you see a grinding machine, you see a hammer, and you have the torch, because even if the steel doesn't need to be preheated, you must remove the moisture if you follow the codes, the D1.1 codes, for example, AWS. And after each pass, normally, you have to remove the slag. So you need a hammer, or you need a hammer, and remove the slag. Here, if you take your ear close to the window of the Jimao, in the Jimao in your room, you don't hear anything. You just hear a little bit how they are doing the welding. You don't hear hammer. So they are not removing the slag. So that means in all the welds today, you have tiny cracks. Unfortunately, and it's the same in Beijing, it's the same everywhere in China of what I've seen, you need a catastrophe. You need a big earthquake, and after that they will change the codes. After that, you need also to grind the weld to make a smooth weld and to do the next pass. And after that, there should be an inspector on the job site who will do a UT test. If you have a full penetration weld, you must do an ultrasonic test. When you talk to a steel fabricator in the United States and when you ask them, how many times do you have to repair the welds? They say about 10%. 10% they have a defect, then they have to grind and then refill and then correct the weld. When I ask Chinese steel fabricators, how many times do you need to repair the weld? Do you know the answer? Never. So I guess that in the future it will be a big problem once we will have a big earthquake here in maybe Beijing. Beijing will be the big one, and maybe in Shanghai. So today, I don't know if you know, but we have a high-performance steel available today, and since the 90s, we have even 465 megapascal steel, which is produced with a quench and self-temper material, which have a very good ductility and a very good weldability, which doesn't need to be preheated. This building, for example, was built with roll sections, and I think here, this is one of our sections in the column here. So it's a very safe building, this one. So we can produce, and steel today are available in different grades. You know, in the Chinese grade, and it's the same in Europe, the yield is decreasing with the thickness of the material. If you have thick material, the yield is decreasing. But in the United States, we can supply a steel with the same yield for all the thicknesses. So here it's maybe the most technical slide of my presentation. So if you understand this one, you should be able to understand all my presentation. So here you have the yield of the steel. And on the vertical axis, you have what we call the carbon equivalent. The carbon equivalent is a measurement of the weldability of the steel. And the carbon equivalent is this big formula here. So when we have to change the yield of the steel, when we have to increase the yield of the steel, we have to change the chemistry of the steel. We have to put more alloying elements into the steel. And if you use the classical way of doing steel, what we call the thermomechanical steel, you have, for thick material, you have to change so much the chemistry that the steel is not weldable anymore. This is why you have to preheat the steel before welding. By using the quenching and self-tempering process, we can produce high-strength steel with a very good ductility and a very good weldability. This is an example of a splice in a jumbo, which is, I think, what we have supplied here in this building. So this is 125 millimeters thick. If you use a normal 355 megapascal steel, or if you use plates, Chinese plates available here, you must preheat that at 110 degrees before welding it, before the first pass. So it takes about 5 hours with a torch. Just doing that with a torch, 5 hours. And then to do the welding of that, do you know how many passes you need? Okay. Can anyone guess how many times you need to do that? So it's 140 passes. So it's a lot. Right? And it takes about 8 hours. 8 hours for one jumbo like this. Now imagine the huge caissons, because they are using also 65 mm plates. To do the welding, if they really follow the rules, it will take days. And I checked, I came 2 days ago, they did one in one night. One caisson was welded during the night. We can supply heavy sections like this up to 140 millimeters thick, and we can go now today up to 485 megapascal. So this is the heaviest, what we call jumbo. And this is the heaviest beam, so it's a W36, and it's 1,377 kg per meter. So you can use that, and it's a finished product. So instead of using these huge caissons, in LRFD today, they say you can use composite design with untied sections, build-up or roll sections inside the composite section, as long as you check that there will be no buckling of the individual member before the concrete is dry. This is the only thing that you can find today in the LRFD design code. They do not explain how to do the design. So we developed a method to replace all these caissons by using roll sections, and we are exactly following all the rules given in LRFD or ACI 318, And they are based also on the examples given. You can download them. It's example number 14 from AIC that you can find on the web of AIC. So we have developed this method to calculate the sections, to calculate also the stud connectors, or the plates, the stiffeners, in order to transfer the loads. So we don't see it very well here, but we can use here double layers exactly like in the Shanghai Center, or single layers. The advantage of using a roll sections is that you can lift 3-4 floors at once with a 20-ton crane, instead of lifting one floor by floor and to have to splice every floor. This is the Freedom Tower. This is 541 meters. The World Financial Center, it's 496 meters. Here in this case, they are not using big mega columns into the corner. On top of that, the architect, they should not put big columns into the corner. If you want to rent an office, if I'm the boss of an office, I want a corner office with a window on the left and the right. If you put a big concrete composite column into the corner, you are wasting the most expensive place into the building. So here in the United States, they always try to avoid columns into the corner to have the best view as possible. For this column, they use in the basement of the World Trade Center 1, so the Freedom Tower, they use 460 megapascal jumbo beams, the same as in this column here, and then welded plates here, special plates in 460 megapascal. This is 30 meters, just one column, or erection of one column. And to do the welding here, the port authorities say this doesn't need to be preheated because it's a quench and self-temper material. This needs to be preheated according to the codes to 150 degrees because it's 460 megapascal. So they had to preheat everything at 150 degrees. And the port authorities say you must preheat everything just to be double safe. This building is the safest building on Earth today. And you know how long it took them to do the welding? 7 days, days and night, following the codes. I ask here different steel fabricators in China, they say, oh, less than 1 day we do it. On top, when you splice all this column, don't put all the welds in one plan. Because if something happened to the weld, the crack will go through one plan. So in the Freedom Tower, for example, when they are splicing the jumbos with the plates, so they put the weld of the plates here, and they are welding the jumbos here. So they put the welds at two different locations to have a much safer structure. This is what Northridge taught us. When you have to splice two jumbos, you must do what we call a rat hole. Access web not to put weld in this region because you have high level of stresses. When they weld the caissons, first they do not do a bevel. The code says above 10 millimeters, you need a bevel if you want a full penetration weld. Here they are welding just a small gap, filling a small gap between two heavy plates. So you need to do that, and you need to do this type of hole to limit the residual stresses once the weld will shrink. So this is how the splice will look in reality. So you have two jumbos. This will be removed, and this is the type of typical splice that we have seen for many, many years now. So this type of connection, we can teach them easily to the inspector on the job site here in China, and he will see, this is how we have to do it, and then they will apply it easily. So now I'm coming to this method. So this is technical. I hope you are structural engineer now and not only architects in the room, otherwise you can leave and go somewhere else. so we developed this method. It's about 70 pages that you can find on our website, or you can ask me, I can send you a copy. So we did 4 different examples. One according to the strong axis, one designed the NM curve according to the weak axis, and then two design examples to calculate the shear forces. So So we use not the new things, we are just using what is existing in LRFD or ACI 318. So you know that Royke and Beckman, if you are an engineer, in 92, they invented a simplified method to calculate the NM curve. We are using exactly the same thing. So the NM curve is something like this, when you have the axial forces with the bending moment. And Royke and Beckman, they say, instead of calculating all the points, we calculate only four points here in this curve. And then we do a straight line, and then we can have the NM curve. So without going into detail, we are describing the method, how to find this NM curve directly using different jumbos, multiple jumbos into the composite sections. So we do that according to the strong axis, and after that we calculated the NM curve, and we also did some finite element analysis to prove that our simplification using this method was correct. So you can see here the finite element analysis, and here you can see the simplified method. So we have, after that, the LRFD design, you have safety codes, so you apply them, so you obtain this curve. And if you use the ASD design, you have a smaller curve. Okay? So it's not too complicated. For the shear forces, so we did the same in the weak axis, but for the shear forces, AIC is telling you have three options when you design a composite section. So you can use the available shear of the steel section alone, so you neglect the concrete. But once you have a big concrete column like this composite with small shapes inside, if you use that, you are missing a lot of possibility to transmit the shear forces because you are neglecting the concrete. So this option is not really the best one. If I take the third one, the available shear strength of the steel section in addition to the reinforcing steel, ignoring the contribution of the concrete. This is not okay because when you use untied sections, so you have something very weak or weaker, the concrete, very strong, the steel, then in between something weak. So when you have shear forces, something very strong and something very weak, the weakest point is the concrete because it's in between. The steel and the concrete are not working in parallel. They work more like in series. So you cannot use this option 3 because the weakest point is the concrete in between the two beams. So the option 2 is to say we are using the reinforced concrete portion alone, and we use ACI 318, which is the best solution and the only solution. So we developed, and I will not go into detail here, how to do this equivalent concrete section. So you know, once you have a composite section, the shear forces can be proportionally distributed according to the stiffness of the different portion. So you have this portion here, it's only concrete. So then you use ACI 318 to design it, very simple. This one in the middle, it's also concrete, so it's easy. This one is the most complicated one because you have concrete, steel, concrete. So the idea is to say, okay, I'm going to replace the steel by concrete, by equivalent section in concrete. So if I take this section here, and if you replace it, so you have concrete, you have the rebars, you have the beams here, convert it into concrete. It's a simple method. Then the concrete, and then again the steel. So when you have the shear forces, so we are also calculating the number of stud connectors that needs to be put here and here to determine. So we give all the methodology how to calculate all the shear forces. Because if you have the shear forces like this, you have the same shear forces like this, so you need stud connectors in the other direction to distribute the shear forces on the longitudinal axis of the column. So we are explaining how to calculate these stud connectors, and we are also checking at this zone how many stirrups or how many ties you need also to distribute the shear forces into the concrete. So everything is explained. The same thing in the other direction. So we are replacing, for this zone, we are replacing the steel by concrete, and we are measuring here in different sections all the shear forces to determine the amount of stud connectors and the amount of ties that you have to put. Another solution is to use, instead of stud connectors, is to use a plate. Because if you have a composite column like this, how to transmit the forces from one beam to the other beam is to use, if you use plates in the chamber of the beam, you will have like a truss in concrete inside the composite column. So we are designing this truss here using a very simple triangle equation to find the loads that should be transmitted through the truss, and then we determine the amount of ties that we need to put into the composite column. So then the method is not a new invention, it's just using simple equation from LRFD, ACI, and based on examples existing in AIC version 14, and then with that you should be able to design much safer buildings than what we can see today. There was one example like this. I don't know personally who was the designer because this is not our steel. This is Japanese steel, so we cannot win all the projects. But they use the same concept. This is IFC2 building in Hong Kong. Very nice concept using multiple shapes. There are build-up sections here, not shapes. But they use the same type of concept using multiple sections. And you can see it's very fast to erect, much faster than what we can see next door, because you take one beam and you have immediately 3-4 floors. And you see it's untight between the floors and just putting the transversal beams to tie them on the floor. Okay, so you can go on this website to download the full design method, or you can just ask me and I will be happy to send it to you. So thank you very much.